Hello everyone. Am I audible? Okay, so I'm Simran and we'll be having a live session today We'll be solving some problems related to week 2 content of control engineering course. So I think you all have gone through the lectures related to Laplace transform and LTI system representation using Laplace transform. We'll be doing questions related to that only. And apart from that, whatever doubt you have, you can ask in between. Okay. So we'll wait for a few more minutes and then we'll start. Yes, Suman. Yes, Suman, you have raised your hand. Okay, fine. So I think we can start now. Now the problems that we will be dealing, so we have to assume that all the signals, yes, I couldn't hear you. Can you repeat? PDF will be shared after session only it will be shared, no? Okay, so for all the questions that we'll be solving, we'll assume that the signals are causal. That means their value is 0 for all time t less than 0. Now, unless stated otherwise. Okay, so first question is this one. This is all the questions are related to week 2 content of the course. So we have been given a function and it is told to find the Laplace transform of this one. So the function is f of t sine omega t cos omega t. Now, in the lecture, you all have studied like for standard signals. For example, like there are some signals for which Laplace transform sir has derived. So from there, and also the properties of Laplace transform that is discussed in class. Using that, we can solve this signal. So, what is the Laplace transform of sine omega t? It's omega by s square plus omega square. We also know Laplace transform of cos omega t. This is s by s square plus omega square. Now, if a signal xt has Laplace transform xs, then txt, its Laplace transform is dxs by ds minus dxs by ds. So from here, we can find the Laplace transform of this signal. Suppose this is x1t and this is x2t. So what will be the Laplace transform of x1t? Minus d omega by s square plus omega square by ds. And if a signal has Laplace transform xs and it is shifted, or you can say it is multiplied by some exponential, which part you have confusion? So these things, this is the property of Laplace transform. Let me share the screen. There are several properties related to Laplace transform. Can you see this screen? I think is this picture? So similarly, like this is a property, no? Like this thing, I like there is some dual properties, okay? Now when you are multiplying time in this domain, okay, then there is differentiation in frequency domain, or you can say in S domain. And if we are multiplying S in the S domain, or you can say Laplace domain, then there is differentiation in time domain. So it's kind of dual property. Now derivation of this is formula based, so you will apply the basic definition, no? Xs equal to xt to the power minus st dt. So from there, if you multiply txt, okay, should I explain the properties? Okay, fine. So first property is linearity. So suppose there is x1t is a function which is having Laplace transform xs, and x2 is another signal having Laplace transform x2s. Okay, this is x1s and x2s. So alpha x1t plus beta x2t will have Laplace transform alpha x1s plus beta x2s, which suppose this ROC of this one is R1 and the ROC of this one is R2. So the ROC of this one will be R1 intersection R2. Now this we can see with an example also. So if there is signal e to the minus 2t ut, ut is unit step. So basically this one shows that this signal, this will start from t equal to 0. Okay. And there is another signal e to the power minus 3t ut. And suppose there is coefficient 2 and 4 like this. So this is the overall signal. Now, if we see this signal, its Laplace transform will be what? 1 by s plus 2 multiplied by 2. And its ROC will be, because this is a right side signal, no? Right half plane signal, you can say, because it is propagating towards with increasing time. So the ROC will be right side of the pole. The pole of this one is when where the denominator is 0. So s plus 2 is equal to 0. Uh, 1 minute, 1 minute. Yes. What is in left side? This pole is in left side. So s is equal to minus 2. Now in s, okay. So now in s plane, what we have? There is one pole at s equal to minus 2. So for all the values of s, which is right to this axis, which is parallel to j omega axis, this Laplace transform is defined for this signal. Okay. So that's what I told, na? ROC R1 and ROC R2. So this is R1. And then you have another signal which is 4e minus 3t, no? Ut. So for this, what will be the Laplace transform for s plus 3? Now what will ROC of this one will be what? It will be all the values to right of minus 3, no? This axis. So real part of s should be greater than minus 3. Okay, now this is sum of these two, this xt. So what will be the Laplace transform of xt? This will be 2 by s plus 1, s plus 2 plus 4 by s plus 3 and this intersection minus 3. What will be the intersection? This is minus 2. ये ऐसे था. तो ये वाला greater than minus 2. The real part of s should be greater than minus 2. Is it clear up to now? This is linearity property. Okay. This one. And also this intersection is valid. Fine. If you say that you have one, there will be some signals in which ROC is not defined. So Laplace transform. Suppose there is a signal such that its ROC is like this. And there is another signal which ROC is to the left of this. So which type of signal it is? It is like non-causal signal, which is having value in with decreasing time. Okay, it's like left. So it depends, no? Where is the value? So if the intersection of these two contains this one, like there is some region which is coming inside these two, intersection of these two, then we can say, okay, Laplace transform is defined and ROC is this one. But suppose this is minus 3 and this is minus 2. So, yeah. No, that is for a stable system. That for a stable system, j omega axis should be contained. Now for if this is minus 2 and this is minus 3, so we are saying this ROC is greater than minus 2 and this ROC is less than minus 3. So it is like this. What will be the intersection of these? There is no intersection. So here Laplace transform is not defined. Okay. This is one property. Then suppose there is a signal xt. It has there is another property which is time shifting. So it has Laplace transform xt, which is xs. Now it is shifted. So its Laplace transform will be this one, and real part of this will be shifted. So its ROC is R, like suppose. It will be shifted by T0, I think. Let me check. Okay, fine. There is some shifting. Fine. No, its ROC will be same. Sorry. Hai. In case of frequency shifting, ROC will change. Okay. So for this, should I also give example, or you can just simply make an example? Suppose this is the signal, and now you have e to the power minus 3 minus t minus some, you can say 2 ut. So earlier it was u t minus 2. So earlier it was starting at t equal to 0. Now it is starting from t equal to 2. It is shifted. So ROC is, its ROC is s plus 3. Sorry, Laplace transform is s plus 3. So its Laplace transform will be s plus 3 e to the power minus 2s. Okay. Is there any doubt in this? Now, third one is frequency shifting. So suppose there is signal xt and it has Laplace transform xs with ROC R. So here ROC is not changing, it's same. And if it is multiplied by some e to the power s naught t, suppose. Frequency multiplication, basically you are saying. E to the power minus at. So ROC will be shifted by real part of s naught. Okay. Now similarly, the differentiation property, it's like if you see, basically what we are doing, there is a signal xt. So say like if for communication purpose, what happens when signal has to be sent to some other place or something? So that has to be embedded in a high frequency signal. So if there is signal which has low frequency and they just suppose cosine wave with high frequency, suppose 100 hertz, and the signal is of 1 hertz. Then multiplying this cosine wave with this one, it's called frequency modulation. This will shift this frequency content. Means this information will be shifted to this frequency. Then similarly for multiplication by t, if we have t multiplied to xt, so it will have dxs by ds. And dxt by dt, if there is differentiation in time domain, So it's a multiplication in frequency domain. Now this one is valid if initial condition is 0. If initial condition is not 0, then we have x0. There is one scaling property also. So if x is 80, x80, signal is compressed or expanded in the y domain, like y across y axis. So it's like signal is like this. Now signal is compressed or it has been expanded like this, or it has been compressed. So it will be like this. These are some of the properties. These are already discussed in the lecture. So should we proceed to problem, or you have any doubt related to this? Okay, fine. So here we will be using the property only. So if we have sine omega t, we know the Laplace transform of this one. Then t sine omega t will be what? This derivative in the S domain. And we have cos omega t, we know the Laplace transform of this one. Then e to the power minus 3t, this is multiplication by exponential. So this is basically shift the S domain. So it will be, I think, minus 3 or is plus 3. Minus 3 though. So we'll first differentiate with respect to this. So minus 1 omega y s square plus omega square. What will be this? Okay. Yes. Why it is differentiation with respect to s? Now, suppose you apply chain rule, okay? So d of omega s square plus omega square dy s square इसके रिस्पेक्ट में करो एंड फिर देन डी एस स्क्वायर प्लस ओमेगा स्क्वायर बाय ds. So it's like इसको u consider करो, then consider this as u. So what will be this? Omega ut minus 1. So minus omega by u square. Is it clear? This simply chain rule. So it will be like omega by u square. No? So u is s square plus omega square. And already there was one minus, and you have got one more minus. So that is plus, and this one is 2s. Okay. Any doubt in this question, or should we proceed to next one? Okay, then we'll proceed to next one. Now there is a differential equation, basically ordinary differential equation. And here we have linear ordinary differential equation. Because all terms are linear in y. Okay, now we have to solve for y, like assuming all initial conditions are 0. And hint is to use Laplace transform. Obviously, if we try to solve this one, we have to do lot of integration if we go through time domain. So for that, we'll be using Laplace transform because it will change it to algebraic and all, and it will make it easy. UT is unit step or step input. So what will be the Laplace transform of this one? Now this is d2y by dt square. This is second order differentiation of yt. So this will give s square ys minus s y0 minus y dash 0. Y dash is differentiation of y with respect to t. So y dash 0 is equal to what? dy by dt at t equal to 0 plus 4 dy by dt is Laplace transform of this. Basically, we are applying Laplace transform. Plus 3 ys equal to 2. And unit step, what is the Laplace transform? 1 by s. Now it is saying all initial conditions are 0. So this will be 0. This is also 0. What would we get? S square plus 4s plus 3 ys equal to ys equal to 2 by s square plus 4s plus 3. Now what we have to do? We have to split this one. Is this splitting correct? So if you multiply this s square plus 4s plus 3, fine. Now how we add so that this is equal to 2? That we have to see. So what should I write here? What should be the value? Or we can do what? We can simply say that suppose this is A1, A2, A3. So A1 will be equal to multiplied by S at S equal to 0 because here the pole is 0. S से S गया and this will be 2 by 3. So A1 we got. For A2, this will be 2 S plus 3 S plus 1 multiplied by S plus 3 with S equal to minus 3. What will be this? Minus 2. I think this will be 1 by 3. E3 will be is equal to -1. -1. So this is 2 by 3s plus 1 by 3s plus 3 plus -1 by s plus 1. So now we will take Laplace inverse of this, or inverse Laplace transform. So what will be the yt? Let's see if we got the answer. Answer is 2 by 3 minus e to the minus t. Okay. And then plus 1 by 3. I don't understand. Fine. Now, since ut is being used because all these are causal signal. Is this fine? Any doubt in this question? Okay. Now we have to find ROC of Laplace transform of this signal. So what would be the Laplace transform of this signal? It's same as I explained earlier. It's linear combination of two signals. We know Laplace transform of this. We know Laplace transform of this. This will be sum of these two. And we have to find ROC of these two so that we can find intersection of ROC of these two. Now we know that the signal is causal signal, so it is a right-sided signal. For right-sided signal, ROC will be greater than this and right side of this one. For this one also, it's -4, so it will be right side. Intersection of these two, ROC will be on right side of this axis, which is real part of S greater than -2. Is it fine? Am I audible or not? Okay. Now, this is a transfer function of system, and it is said that these are not equal to 0, these coefficient. And one of pole of the system is -5 plus 7i. So we have to find the coefficient. Now, this is an algebraic expression, and we know that a, b, and this coefficient 1 are real numbers. So for real numbers, whatever the roots are, either it will be a real, or even if it is complex, then the roots will be complex conjugate. Okay. So if this is one root, so this is S domain, no? S domain, this is the root, -5 plus, this is -5, the real part of S, and this is imaginary part of S. Or you can say sigma and j omega axis. Okay. And this is 7i. So this is the root. Now, if this is one root, this is complex. So there will be another root which is complex conjugate of this. It will be this one. So this will be -5 minus 7i. So there are two roots that we know, and this is a quadratic equation. So it will have two roots only. So these are the roots of this equation. So S minus -5 plus 7i multiplied S minus minus 5 minus 7i. Now we have to multiply this. So these two will cancel out. And what we get is s square plus 5, 5, 10s minus 7i square. So I squared is minus 1. So this will be plus, and 7 square 49, no? Plus 25. 594. So this is one coefficient and this is another, A and B respectively. So what is the value of A and B? 10 and 74. This is what we got. This is the correct answer. Any doubt in this question? Okay, then we'll move to next question. There's this spring mass damper system with friction in it. And what is the input to the system? Force, which is the external input that is given to the system. All others are internal forces that are acting in the system. And then what is the output? X, which is the displacement. This is the output, this is the input. Now we have to find the transfer function xs by fs. So for this, what will be the dynamics of this system? This will be mx double dot, whatever kinetic energy that is assigned to the system, that will be because of force that is being applied, minus this force will be used to overcome the friction, or you can say damping forces. So this will be bx dot, which is velocity, because the damping force is damping coefficient into velocity, minus f, and some energy will be stored as potential energy, so kx. So we can write this as mx double dot plus on it also, bx dot plus fx dot plus kx equal to f. Now we'll simply apply Laplace transform, assuming now since we have to find the transfer function, no, the transfer function is what? Laplace transform of output divided by Laplace transform of input given initial condition is 0. So if we apply Laplace transform of this one, we have, because earlier we had seen if it is x double dot, so we have s square xs minus x0 minus, sorry, sx0 minus x dash 0. Now initial condition will be 0, so we'll just have s square m xs plus s b plus f xs plus k xs equal to fs. So this is the transfer function. This one. Any doubt in this question? So given any mechanical system, you can model these dynamics, no? Now there is this Laplace transform which is given, and we have been told to find initial and final value. So we have this initial value and final value theorem using Laplace transform. So can you tell me what will be the initial value using Laplace transform? What is the formula? Anyone? This is a week 2 content. Its limit s tends to infinity as excess. So let us apply this. Is it correct? So if we apply s equal to infinity, this will go to 1. And for final value, that is the steady state value, you can say. This will be limit s tends to 0 as excess. What would be the value? This is simply 0. If we put 0, 0 everywhere. So this is the answer. Any doubt in this question? Okay. So this is one question. Again, we have to find inverse Laplace transform. So similar to Laplace transform, we also had properties for inverse Laplace transform, which is same like linearity and then scaling, time shift, all those. So we'll apply property here also. Now, if you see, this is the signal. So this is something like 1 plus s square 9 if we start from here. So what will be the Laplace transform of, sorry, inverse Laplace transform of this one? And then we have, in place of s, we have s plus 2. Again, there is this multiplication with exponentials. This is phase shift in frequency domain, or you can say Laplace transform. That means time shift in time domain. Okay, so we have different like numbers of properties related to inverse Laplace transform. Now, one property is xt if the this is a transform, you can say, and then we have inverse Laplace transform xt. So if we have s plus a, you can say shifting in Laplace transform, then it is xt e to the power minus at. You can say like this. Like we had no in Laplace transform that xt, then we have x's corresponding to this. If we are multiplying with this exponential, then there is a shift in frequency. So it is saying same thing, but it is just reversed. And then if this one is like xs e to the power minus st naught, so this is x of t minus t naught. Now this is one signal, means Laplace transform of a signal. We get this signal. Now this Laplace transform has been modified by taking s plus 2 in place of s. So we can say it is like this. This is xs. So now this is s plus a. A is minus 2. So we can keep it like this. I think this is x minus a. Maybe there's some sign mistake or what. But this will be giving this one. So earlier it was this. Now this will be multiplied by exponential. Now this is your new Laplace transform. Now suppose this is the base transform, and on this we are again modifying this with multiplication with exponential e to the minus s. So when we do this, it will go to this one, t minus t naught. So this will shift. Is it clear? I think this is s minus a. Huh, okay, I have. It's a writing mistake. Fine. Now whatever Laplace transform we have, so how do we define that? Like if we have some graphical representation of that, so we do this by pole zero representation. Okay, so we have a pole zero plane, that is a S plane. In that we define where are the poles and zeros of the this transform, or we can say this transfer function, because we when we are dealing with system or dynamic system, we are saying okay, first we thought that okay, signals are made up of sinusoidals. Now this was not enough, because for some dynamic system we had this decaying thing, so like this type of signals. So if we consider sinusoidal, it's an oscillatory signal, but it's a damped signal. So for representing this type of signal, we turn towards Laplace transform. Now that Laplace transform we are using to find the characteristics of a system. So we are using what is the input-output relation of a system. So given an input, what will be the output? For linear system, we say, because if you have gone through basic signal and system, so if we say delta t is an input, which is an impulse, unit impulse you can say, and it has output ht, which is unit impulse response. Now any signal xt, it can be written as summation of this one. Like if we consider a discrete system, so suppose xn. Summation. So at every time instant there is an impulse, and this impulse is weighted with the value of the signal xt at each time step. So this is one of the things that every signal can be expressed as a weighted sum of this unit impulse. Now, if we know what is the response of system to this unit impulse, which is hk, then we can find out what is the response of system to any given signal, because that signal can be represented at the weighted sum of this one. Now this is linear system, so output will also be a weighted sum, because we know from linear system thing that if xt is one signal and yt is another signal, and its output is at, suppose, and its output is bt, so any linear combination input of this will give same linear combination of this. So alpha xt plus beta yt will have output. If it is given to linear system, it will have alpha at plus beta bt, this one. So once we know response to unit impulse, we can find response to this one. Now this is in time domain, we'll have to do convolution, because this is a type of discrete convolution. And what you have seen, this x tau h of t minus tau d tau, which is in unit impulse response of system. And you do integration 0 to infinity, then you get yt. So this is a convolution thing that we perform to find the response. Now this is computationally expensive, so what we try to do, we have this Laplace transform tool with us, so we try to utilize this. That why to go through this lengthy procedure, we will simplify things and we'll just see Laplace transform and find out. So this Laplace transform for system, what we have defined, this is the Laplace transform of output yt. If this is the system which is given xt and output is yt. So Laplace inverse of this divided by Laplace inverse of xt with initial condition 0. Because if initial condition is not 0, we will not be getting this Laplace transform. There will be some initial condition and all those things. So we consider this, and this is a way of writing what is this transfer function. This is this one. We can say this is basically the response to unit impulse in the system. So if we are saying y barabar g, y x equal to g, so y equal to g into x. Now what is the Laplace transform of unit impulse? This is the x input, this is unit impulse. Laplace transform of this is 1. So y is g, simply Laplace this transfer function g. So this one is the Laplace transform of response of unit impulse to the system. Unit response is basically a shock, or you can say perturbation, like sudden perturbation, you can say. So now we are characterizing this response of system to unit impulse in frequency domain. And if the initial conditions are, suppose, yes, yes, no, there is no group created for this one. So this problem session is just to make you more so that your concepts are more clear. The PDF will be shared through the site only, so the that concerned authority will share this with you. Okay. So now suppose we have the Laplace, transfer function of this one. So we know this is impulse response. Now we have any signal and we know the Laplace transform this one. So what we have to do? We don't have to go through this convolution equation. We will just simply multiply this with and we'll get the output response. Also from Laplace this transfer function, what you can see, if there is no input also and there is some initial condition of the system, then what will be, how the system will behave. So that will depend on what is the roots of this. That means poles of this transfer function. If poles are negative, so it's like you had seen e to the power minus at ut. This is a, suppose this is a signal. So what was the Laplace transfer? 1 by s plus 1. Now, what is the pole? This one, minus 1. So, if the pole is minus 1, what will be the like response to unit impulse? This will be like this. So, any initial condition x0 or y, x0 means here output is y0. So, that will evolve like this, y0 e to the power minus at. Okay. So for this, from the poles, we can do analysis of whether the system is stable or not. All those things we can do. Now, the whole lot of concept, already you have learned a lot of concept through lectures. So we'll do the question. Now we have to find the zeros and root. So what is the zero? Zero is any value of s where this gs becomes, value of gs is 0. So for what value of the s this will be 0? So simply if we say minus 5. So this one is this, and for poles we have to factorize this. Now one pole we can see if we keep 1 1 1 everywhere, or we can say minus 1. 1 will not satisfy this. This is not equal to 0. So minus 1 will satisfy this. So we can find the another rate, simply divide this one by s plus 1, because this is one factor. Minus 1 pole is 1. So s plus 1 is one factor of s square plus 6s plus 11s plus 6. And whatever you get, that will be a quadratic equation. From there, you have to factorize it and you'll get another, like other roots. So and this will be s plus 2, s plus 3. So roots are minus 2, minus 3. Now this is, there are three roots we have found out, minus 1, minus 2, minus 3, and 0, 0, minus 5. Okay, so we'll proceed to next question. So now we have convolution, like you have to apply this convolution theorem basically to convert it to Laplace and then find the inverse Laplace transform of this one. So e to the power okay, let it settle. In meanwhile, you can ask any doubt if you have related to lectures. So where to find convolution? We'll just find Laplace transform of this. So it will be the multiplication of yes. Okay. So from this one, suppose xt is a signal and yt is signal, and like you do convolution, so you can write that suppose zt is the output, zt is xt convolved with yt. So it's like x tau y t minus tau d tau. Basically, you have gone through that slide, no, which sir has taken, that there is one square wave, or you can say there is another square wave, same. Now you have to find zt. So this will move from minus infinity to infinity. Now when it is minus infinity, it's not like, what is the value of this signal? This is simply 0, because this is having value at here. This is 1. So this will be 0 like this. And when it start passing through here, so it has some value. And this will increase like this. Once it is at half, then again it moves and it comes outside this square, this one. So outside this square, this is again 0. Maybe I'm not able to explain properly. Okay, so basically what we are saying, that this is one of the thing from system perspective. If you see, so while finding the response to the system, what you say, that you have a signal xt and you are finding the output yt, and yt is basically what? Xt convolved with impulse response of that system. Now instead of like because that is convolution thing, you will vary tau from minus infinity to infinity and you will find all the values. So if we go in Laplace transform, it will simply be multiplication of transforms. Okay, for from zeros, let me finish this question, then I'll explain that. Okay, because that he has doubt in this, no. So from convolution theorem, what you get, that if xt is convolved with yt, then Laplace transform of the signal zt will simply be multiplication of this Laplace transforms of these two signals. So this is the Laplace transform of this one and this. And we'll simply factorize these two. So this is 2 or 4 like this, and you'll multiply these two, you'll get s square plus 4. Then factorize this and you'll get the Laplace inverse of this one, take, and you'll get the answer. Okay, so is this convolution doubt clear? Convolution theorem? Okay. Now coming to pole and zero, so basically in context of this systems, when we say that a system or LTI system, basically we are dealing with LTI system, because if it's not time invariant, then we cannot define this transfer function. So for this LTI system, this poles basically represent, means we can say what is the, when the input is 0, means no input response, or we can say 0 input response or natural response of the system. So suppose that there is this pendulum, Now we are approximating this pendulum, means linearizing this pendulum about this equilibrium point, because this pendulum had two equilibrium at this location and an upright location. So it's zero, angle zero, velocity zero, and angle pi, velocity zero, these two. Now this equilibrium point, if we see, now this is a linear system. If this system is perturbed, suppose ऐसे force दे दिया, ये lecture में भी बताया है, but suppose ऐसे ही force दे दिया, sudden force. So how it will evolve, how this system, because there is no input, just a perturbation. So this is kind of an impulse, sudden input जो है. How this will evolve? So its initial condition is this now. Now this will try to move like this. If there is damping, or we can say this resistive force, then it will go and settle to equilibrium. So if it settles to equilibrium, what we say, that it has come to its equilibrium point. Now it will not evolve from here. So this is an stable equilibrium point. So from poles we can find whether the system is stable or not. Another thing is, basically stable or not, because we know that what is the response to perturbation for linear system. And now since we are saying response to perturbation, because this is a linear system, this will be the global response. It's not local response, because uh, I mean, for linear system we are linearizing at this point. But if we take like non-linear system, there are various equilibrium points, and corresponding to each equilibrium point, we have to define the stability and instability like that. So there we can linearize the system, and there are some conditions like eigenvalue, or we can say poles of that system. We try to find out. Regarding these zeros, so it's kind of like, we can say, regarding the pole, is it clear? Hmm. Hmm. Okay. So regarding the zeros, it's kind of adding a derivative, like rate of change so output response. So it's like we have 5 by 10, 6s square plus 11s plus 6. So whatever the response we are getting here, and this is being multiplied by s. So what does this mean? There is a derivative term is being added to the output. So suppose this is the input, it has one response, and there will be some derivative. Suppose a function is like this, and how would it derivative look? It will be looking something like this. No, it will also settle to 0 after j. So the response will be sum of this one and this one. Yeah, like this one only. Also, when the poles are at right half plane, so we define the systems as minimum phase or non-minimum phase, basically the lag of the system. So if the poles are in left half plane, then the lag, basically these are causal system. No? So when we give input, output will be observed after some time. That is the phase shift with frequency that we say. So this will increase if the zeros are in right half plane. As of this, I can recall, but I think I can give more insight on zeros in like next session. Yeah. Is this clear? So now this is the third question. Sorry, last question. You have this input and output is the voltage across capacitor. This is the circuit, and we have to find the Laplace transform of output to input, basically ratio or transfer function we can say. So what we can do, जो basic modeling technique है, कि for each individual element we have to find what is the response, then we'll apply KVL or KCL, something like that. So for this one, if we see for L, what relation we have? V barabar L di by dt. So if we take Laplace transform, what will be? V of L, or we can say is SL IL. So what is the in Laplace domain? It can be represented by SL. Similarly for R, it will be R, and for C, it will be 1 by SC. By dynamics equation, you can apply. Now what we can do, we have to find V out. So we can just take this Z equivalent for this one and find the voltage across this one. This is one way. Another way, we write the dynamics. So suppose this has I1 and this has I2. What we can write? V in minus L di1 by dt minus R I1 minus I2 equal to 0. This is one equation. For another circuit also we can write R I2 minus I1 plus C. What will be the equation? I barabar C dV by dt, no? So V is equal to 1 by C I dt. These are two, and V out is simply voltage across this. So this one. Now we can apply Laplace transform to these two equations because this is di by dt. So we can write it in S I, and then this will be simply I1s I2s. Here we will have 1 by SC I2 because this is I2, and we'll get equations in Laplace transform, and we'll solve these two equations to get V out by V in. So if you solve this, it will come like this one. You can try this by your own, just writing the equation and simplifying this to V out by V in. Okay, so any doubt in this question? Fine. So if you have any doubt related to lectures, you can ask. I'll just recall. Assignment means the assignment uploaded on the website. No, I'm asking which assignment are you asking? The assignment uploaded in website, no? Regarding that, I don't know. Maybe you can ask a question like in the ask a question or Google group that whether it will be provided or not. But yeah, if you have gone through this live session, I think you can answer most of the question in the assignment. Anyway, when you do the assignment, like then you get the correct answer, no? Like what is the answer to the question? Yeah, we were solving question related to second week, no? But you can ask doubt related to any week. It's not like you have to ask doubt related to second week only. Sample problems that we were solving is related to second week because Laplace transform you have been taught in second week. Next week we'll have for third week, and after that 4 weeks. It's like sequential only. Okay, so frequency domain representation you all have understood, no? That any signal can be, not any signal, most of the signals which exist can be represented as sum of sinusoidal signals. And why do we choose sinusoidal signals? Or we can say sine wave or like cos omega t, sine omega t, like that. Why we are dealing with those signals? So when we are saying no, like we are going to frequency domain or time domain, we choose this sinusoidal signals, sine omega t or cos omega t. We do the frequency domain as well. What is those? This something special about this sinusoidal signal that we are using that for signal like system analysis. And also when we say signal, like when we do signal analysis, then also we say that most of the signal can be represented by sinusoidal signal. So we'll use Fourier transform and all. And then uh, for exponential sinusoidal, we went to Laplace transform. So why not any other signal? We can take a square wave also. We can take a triangular wave also. We can take an impulse function also. No, input can be anything. No, input though you can give any signal. But analysis that we are doing in terms of sinusoidal, mostly when we'll go to frequency domain. So it's like when we pass sinusoidal signal, the output is same sinusoidal signal. There is no frequency change. It's just that amplitude and phase will be changing. Yes. Yeah, this is for LTI. If you go to non-linear system, then if you pass a sinusoidal signal, non-linear system, if you go, then output will have different frequencies. But for this one, we'll have same frequency. It's just that amplitude and phase will shift, and that we will use in frequency domain analysis. Also here, when we are doing S like transfer function, then basically what are we trying to calculate? We are trying to see the response of system to different frequencies of signal. So this is, let us draw Bode plot. Always this opens like this one. No, transfer function from a Bode plot, that is another thing. You have to find what is the value of this gain at different frequency. From you'll find the DC gain, and then what is the where the slope is changing. From there we can get poles and all. But suppose that a system, first order system, it has transfer function s 1 by s tau plus 1. This is one of the system, no? One system. Transfer function having this. Now what we are doing in S plane, if we see, what is the pole? S tau plus minus 1 by tau. This is the pole, no? S tau plus 1 equal to 0. So S equal to minus 1 by tau. This is the real axis, j omega axis. Now how the system will behave to different frequency of the signal. So suppose there is no, like it's a DC signal. So how will we get the magnitude of the output or impulse response, you can say. So this will be the distance from here to here. And as we increase the frequency, this will change this distance. Hmm? So this is the distance of any frequency point on the j omega axis from this pole. And since this is pole, so it is in this one by distance from, this is like multiplication of this omega I minus this pole P. So for different poles, it will have this I will vary and this will be the multiplier. Here we have one pole. So we have distance. Initially it was some value, then it was increasing. That means this is increasing, so this will decrease. So earlier, suppose it is going something like this, little bit constant, then decreasing. So it's like this for amplitude. Now if you see phase, so this is basically angle. So this will change from, earlier it was 0 with axis, then it changes to, because when it goes to infinity, so it's like this, no? Line is parallel to this one approximately. So it's not reaching minus 90, it's asymptotically reaching this minus 90. So this is phase shift, means delay in the system. This is just an example, basically. So Laplace transform, this is how we can do this. Check what is the response pattern. But the reason for using this sinusoidal signal is this one, because this is, the output is very much like the bus amplitude and phase shift, and most of the signal which are there that we see can be represented as like some of the sinusoidal signals. So this can be seen as a base signal, and then we can use that, because earlier also we saw that okay, any signal can be seen as the like weighted sum of this shifted impulse signal. So we are not taking impulse, because then we have to find the impulse response of the system. So, and for this sinusoidal signal, we know it will be of same frequency. This will change as phase and amplitude. So from there we can say, okay, any signal, since we can represent it as a sum of sinusoidal signals. So because it is a linear system, output will also be sum of the response of sinusoidal signal that we can apply. Okay, so this thing then sir has explained, like given motivation for Laplace transform. So basically now we are adding a real axis of the S domain. And later on you will also see that how system stability or causality can be explained using this transfer function. So if ROC is containing the imaginary axis, then we can say, okay, Fourier transform exists, or we can say the absolute sum of the impulse response converges. So this is a stable system, like that. And various like examples for finding the Laplace transform. So these are actually standard signals for which we find, and we'll find that most of the signals are like that only, like e to the minus at into some function, all those things. Because for second order system, we'll have response like this only. We have seen mx double dot, like a spring mass damper system. So it has this response with this exponential multiplied by sine omega t and cos omega t. And then properties of this Laplace transform. So once you go through these slides, or if you have gone through these properties, you must have seen. Any doubt in means these lectures or current lectures that you are going through? What is that? Load pole. Not what I heard. Pole, and there is cutoff frequency or something like that. Load pole, is this related to some particular system? You are saying Bode plot of some system and all. Any dynamic system. That I have no idea. I'll check it and let you know. But generally for a border plot, we define this 3 dB frequency at which gain is decreasing and also cutoff frequency. So this one, this frequency at which the gain is 1 or 0 like this. So basically, since we don't want to do calculations in differential equation, because any dynamic system can be represented as ordinary or partial differential equation. Now, since we are dealing with lumped system or with one independent variable system, so we say that, okay, it is a ordinary differential equation, because there may be some system where there are more than one independent variable. Here it is time. There may be a space also with which it is varying. Like if we say a spread of some disease, so we can see the dynamics of a spread with respect to time, that how it evolves with time, and also how it evolves with different, because in one city it will spread, then it will be transferred to another, like this, no? So how it is spreading through space, those things, so that can be represented as partial differential equation. But we are saying, okay, we have one independent variable, and we'll say that, okay, uh, or we can say that we have lumped the system, so we have got this ordinary differential equation. Now we want to find the response of this ordinary differential equation given to some input, that we call particular response or forced response. So uh, in that case, solving these equations or integral differential equation is not that much like convenient. So we go for Laplace transfer function, means Laplace transform, and then there we just have to, like, basically we have converted it into algebraic equation, because we had d2x by dt square, so we had now s squared xs. So it's kind of change, no? Here we had derivative, here we just have this s square term. So algebraic equation may convert, we have converted. Now that we can because this simplify our calculation. So from there we get the transfer function, and then we have seen the this transfer function is impulse response of the system. After that, there's some examples that has been discussed, and this diagram representation also. There is one more thing, that number of poles will always be greater than or equal to number of zeros, because the system in which number of zeros are greater than poles, that is not realizable. So any existing system cannot have this number of poles greater than 0. So that is one thing. Yes. Question number 10 in assignment 2, the question that I have in my WordPad, or which is there in website. No, sorry, that I can't solve. That is for like you, that you have to solve that question. It has been submitted, but then I'll have to confirm if I can solve that, then I'll solve that in next section. Okay. Next question, I can solve it. Okay, then we went to block diagram representation because any system we can say simply that this is a block in which input is being given and output is obtained. So from there, there are different, this is one of the block, which is summing block. So it's this signal represent, this arrows basically, lines represent the signal and this one is a system. So this is a static system, which is a summing signal, summing point you can say. And the dynamic system that we have, we represent by this block, rectangular block GS. Then we have take up points and all, and we had seen how systems can be connected. So it's kind of series connection if output of one is going to input of another, like that. So in that case, what is happening, just this output is given to this one, so the whole transfer function of these is multiplication of individual transfer function. And this is the case when there is no loading. In case of energy loss or something, this is not valid, so we have to analyze the overall and then we'll have to find the transfer function. Then we had this parallel connection of the system. So output is basically, so this transfer function of this whole block diagram is sum of the transfer functions. And we can have hybrid also, that some is connected in series, some system subsystems are connected in parallel, like that. And one topology that we deal with is a feedback form. So in engineering, we'll be mostly dealing with this one, because our objective is that given this plant we have to achieve a particular, like our objective is to have plant behaving in certain way. So how can we do this? We cannot modify the plant, we have this plant given, so how will we modify? We'll have some feedback included in this, that we will be using to modify the plant. And that feedback here, it has been taken like unity feedback generally we take, and this controller will help in this one. So it's kind of a, we can say we can have this PID controller or league lag compensator, or we can have a state feedback controller. All those things, all those are used in feedback only, so that we can control the performance of the plant. Okay, so this is all, I think. So if you have any doubt, you can ask. Otherwise, we can conclude this session. Okay. Thank you, everyone. Now you can leave now.